Today's lesson is on transients in TESS full-frame images in nearby galaxies. There are a couple of things that you'll want to know before doing this tutorial. We've already talked about some of these. We've used for loops before. We've used lightkurve. We haven't really talked a whole lot about astropy tables or time objects, but we'll do those today. And then the science itself is extragalactic transients, which sounds very exciting. And it is exciting. Supernovae are exciting, but I don't know. I feel like extragalactic transients makes me think of signals, alien signals coming from far away. Maybe that's just me. But the overall focus of today's lesson is not finding aliens. What we're going to do instead is we're going to try to take a table of transients. So we're actually going to use something from the Zwicky transient facility and look at a list of their transients and see if we can find those in the TESS full frame images. So that's I've sort of said like 3 of these first goals all at once, but that's the process that will follow. We're also going to use lightcurve and tesscut to create a background subtracted lightcurve, and that will be our supernova lightcurve. And in fact, we're replicating a figure that was published in a paper, which is linked at the bottom of this notebook. I have some introduction here about what the TESS mission is. I do recognize all of the participant names, so I know that y'all know what TESS is. 10-second summary: surveys in a 24 by 96 degree field of view for 27 days, and then it rotates around and it picks different observation sectors. Because of that, it accidentally observes a lot of interesting stuff because it's constantly pointing around the sky and stares at one spot for so long. And we can use that to our advantage because it will coincidentally point in the direction we would have wanted to look. To get started, we'll do the usual. We're going to run our import cell. Oh, yes, if my keyboard turns on. Run our import cell. There's nothing fancy in here. I think we've used basically all of these packages before. We're just using a little bit more from astropy. So we're using the table and time that's been added to the end there. And we're going to pretty explicitly use the sky coordinate object as well, which I don't know that we've touched on too much. At any rate, we can get started. As mentioned, we are going to be taking the transient table from ZTF. To do that, we're just going to read in a CSV file that they make available. So there's a pretty long URL there, which I did not want to type in. What we will do to get the data from it is say that the transient table, TAB, is table.read, give it the URL, specify the format, which is CSV. And so astropy.tables will read this in, and we can display the table. There are nearly 9,000 rows in this table, so we've got a lot of transients to look at, and there's a lot of pretty helpful information here. They give us the coordinates where it was found. They give us the peak magnitude as well, which is important because TESS is good at finding bright nearby stars, not necessarily good at finding extremely faint, far away signals. So this will limit us a little bit. There's also some information here about the duration, the rise time and the fade time, which, if I'm not mistaken, I wrote down here. Yep. So the rise time is the number of days to go from half the height of the peak to the height of the peak. And the fade time is the opposite. It's the time taken to go from the peak to halfway back down. So you can think about this brightness of this object hovering at background level, going up through half all the way to the top and then back down. So it's just a handy way to think about the curve of this. It's also very, very convenient for us because since TESS is coincidentally pointing at these locations, we now know the window in which we have to look. And we'll use that information later to make sure that we're actually going to find a supernova. Well, part 1 was easy. We got our table of transients. Done. Check. The next part is actually not too bad as well. What we will do is we're going to just get all of the TESS full frame images. If you're thinking, well, why don't we just search on the full table of transients to see? The answer is that query would be really slow. It individually, each query will only take about 2 seconds if you were to feed in those parameters that we see in this table above, meaning like the coordinates and the peak times. But if you have to do that 8,000 times, it's going to take you 18,000 seconds or 300 minutes, right? It's going to take a very, very long time to do it because of the way that we're formulating this query. So instead, we'll say FFIs equals observations dot query criteria. We'll set the project. No, we will not set the project. Sorry, I just updated my. Your materials will not say that. We're going to use obs collection because project is confusing and kind of unhelpful. So obs collection is TESS. Target name is TESS FFI. Close parentheses. We'll print out the length of this. Print the length FFIs. Cool. And then we'll sort the table. FFIs.sort by the minimum time, just for consistency, so that when we print out the first 3 of them, everybody should be looking at the same thing. Because you're not guaranteed to get back these results in the same order when you do a query to MAST. So it is important, if you're using indexing to be consistent, you should probably sort the table. And even then, you have to be careful, right? T-min is sort of a sensible way to do this if you're searching on one mission, but there's lots of gotchas there, so I wouldn't do it by indexing. But anyway, the point is we've gotten these 3 FFIs, and we are going to use some of this information here to help us figure out where the transient events overlap with the TESS observation. We have the coordinates. We know other information like what sector this was observed in and when the observation started, T-min, and we're going to use all of that. So there's information down here about what all of these things mean, which we've talked about a little bit. There's information about how you can use obs_id to parse a TESS observation. We're actually not going to do that because there's an easier way. We'll just find the sequence number. But you could do that in theory. We'll use the sequence number later on. We've got the coordinates. We've got T-min and T-max, which are start and end time respectively, and the S region, which is the footprint or the like the spatial extent of the observation on the sky. And actually, we can take a look at what that means. So if I do FFIs, we'll index with an S region, and then we'll just do 0 to get the first one. This is what it looks like. You get polygon and then a whole bunch of numbers back to back. And really, these are the RA index of each coordinate of a vertex of this polygon. So it's the shape on the sky, right? It's the spatial extent of the observation. We'll plot that. We're kind of doing this in a hacky way. So we're indexing by saying, oh, well, I know that if you split on the spaces, then this term would be 0, this would be 1, this would be 2. And so if I just do 1, 3, 5, 7, 9, I would get all of the RAs. And then if I did the even numbers, I would get the dex. Now, yes, you could do something like start at 1 and do every other to try to create the index. But we also need to convert this into a float because right now it's a string. So we're doing this generator syntax here to create the numbers that we want. There are packages that are actually designed to do this. I think IPyAladdin has a way to parse this. I also think that you can use, there's a regions package. Oh, in fact, I linked to it below. Good job. There's a regions package which does a much better job of handling this. But this is fun. We're just taking a quick look. So we'll do plt.plot example RAs, example explanations. We run this. It's a square. It's a distorted square because we didn't do a very good job of taking what are spherical coordinates and projecting them. We just kind of slapped them into this graph, but it's fine. We can see the square. And so it is a helpful reminder just of how large this field of view is to see the extent of it on the sky from from 75 to 105 decimal degrees of right ascension. And so the takeaway is that we need to make sure that if we're looking for observations, if we're looking for these transients, they could fall anywhere within this square. Now, once again, we're kind of taking a shortcut here. Probably the easiest way would be to think about that anything within 6 degrees of the center is going to be within the CCD's field of view, because that's the largest circle that you can fit inside this square. Now, we are going to miss the corners, which, again, if we wanted to do it right, we would be sure that we got all of the regions of this square. But this is close enough. It'll get us most of the observations, and it will get us to the interesting result at the end. The regions package would do a much better job of handling this. You could also do some linear algebra, but we have an hour together, so no linear algebra. So that's the plan for that. We need to check whether or not they fall within the footprints, and we're going to do that by just a simple, is it far away from the center? Yes, no. Now, we also have to check that it happened at the right time. So it is not enough to say, did transient 1 fall in any of the FFIs that I see? Because it probably almost certainly did, if you think about what TESS has done as an all-sky mission. At some point, TESS was probably pointed in the correct direction. But it's not just enough to have been pointing in the correct direction. You must also have been pointing at the right time. So we need to do both of these things, and we need to do them simultaneously. To do that, we're going to start by creating 2 columns. So I'll do tab.add column. We're going to add some zeros, which are the length table. We'll be explicit here and tell numpy to expect an integer. Never hurts. We'll do a name. It's TESS. How many FFIs contain this target is what that is. And then we'll do tab.add column. Zeros, length of tables is the same as above. D type equals int. But we'll change the name to B N TESS timed. So now this is checking the number that contained the target, and actually we're observing at the correct time to see the transient event. To make our lives a little bit easier, we're going to start using SkyQuard and datetime objects. The first thing that we'll do is we'll go into the FFI table, and we're going to create a new column, which we'll call SkyQuard. We're going to populate that with SkyQuard objects, which are the FFIs. And what I'm doing is taking the RA, SRA from that. I'm taking the declination, STScI, don't forget that. And then we'll specify the units, which in this case are degrees and degrees, because that's how MAST returns results. Okay, good. We're going to do the same thing now, but for a table of transients. So we'll say the table, going to add another column called SkyQuard. We're going to make the SkyQuard objects, the table, pass in the RA, pass in deck, close that next, and then we'll say the units are u dot hour angle, u dot degree, because it comes back slightly different in our other table, so that is important to note. And the last thing we're going to do is the date time objects. So we'll create something that we're going to call peak time. Close bracket. And we'll create a time object, an astropy time object, using the table, the values of peak t. Again, this is just when the transient event is at its brightest. We have to do something a little silly here, which is we're going to add on 2, 4, 0.5800. We need to make sure we're doing this because we're passing this in as a Julian date. And I think that the ZTF uses a slightly different kind of modified Julian date, and so it's easiest to just pass the time object into astropy in Julian date to make the comparison. So we'll run that, and we're good. We've got these three columns set up. There's one last thing that we have to do, which is to think about the times that we actually want to include. What we'll do is filter on the start time of the TESS observation, because we know that if TESS is pointed at a target, it's going to look at it for the next 27 days. So we know that we have 27 days of data starting from that point. What we can do is think about how that would then overlap with the transient event. So we don't want to start too early or we'll miss the whole thing. So we'd probably like to catch at least the first half peak of the object, meaning that we can't, as I've written here, we can't start any more than 26 days before that. Otherwise, we would miss the first half peak entirely. And likewise, we could start as late as the second half peak because we would catch the latter half of the transient fading away. And that's what we're going to do. This code is a bit involved, so I'm going to break it up, but I also didn't want to type it or have you typing because I want you to think about everything that's going on here. So we're saying that we're creating a minimum start time. And what we're doing is, I'm trying to break this up into the individual steps. We're taking our peak times from above, we're converting them .mjd to a modified Julian date. We are subtracting the rise parameter from each row of the table, and we're stripping out this character. I'm going to scroll up just for a second so we can go back to this table that we spit out. So the rise, remember, is how long it takes us to get up to the half peak. Now we have to strip out this character here because we need to parse this into an actual number. But once we do that, we can use this to estimate how long that first rise part will take. So I'll scroll back down. So we take the identified peak time, we subtract the rise because then we know for sure that that's that mid peak point, and then we take off another 26 because TESS will observe for 27 days, so we should be able to catch up to that point. And we're actually going to do the same thing for maximum start. It's the peak time, but now it's plus the fade. So that's what those two things are doing there. And it does look kind of complicated because there's all of this text parsing, but that's what happens when you work with CSVs. You get code that looks like this. Now, as a check, we are going to do an exercise because we've been generating a lot of tables, and we should probably make sure that we haven't messed it up. The task, and I'm actually shortening this, so your focus is just to confirm when the peak of this supernova is. You have the date, but you need to confirm that we've done it correctly in our table. If you have time at the end, you can certainly verify the min start and max start times are correct based on these principles above. But the main task here is to confirm this supernova as this peak date. All right, it is answer time. So this is one way that you might choose to approach this. You could create an index that tells you where in the table you get this matching supernova. So that's the first step that we need to take. The next thing that will actually we can start there. We can take a look at what we've just created. So if we do table and just look at the part where the index is, this is good. This is what we expect, right? We get back all of these values in tabular format. What we're interested in though is we want to know that the peak. When did the peak occur, and does it match this date that I have given here? So fortunately, we have this peak time object, and it's got this number. I'm not quite able to just look at that and tell you what date in human time that is. Fortunately, though, it's not too difficult to get there. So if we take this table, we again do the index, we select the peak time. We've now got this number. But remember, this isn't just a number, right? This is a time, a capital T time object. And since it's because it's a capital T time object, it has a couple of properties, special properties that we can take advantage of. Now, this is not the most beautiful method you'll ever call, but it is a very fast way to get to this answer. So if you do dot year, month, day, hour, minute, second, and you run that, well, there you go. It's given us that information back in precisely that order so that we can see that this occurred in 2023 on June 28th at 11:31 and 12 seconds. And in fact, that does correspond pretty nicely with the date that was given up here. So the point of this exercise partially was just to show you how cool the astropy is. They've got lots of handy features that make it pretty easy to change between different things. Lots of methods that you could find useful. All right, let's go ahead and keep moving along. We're going to do the next step of this. So we've been talking about, we have these two tables, we've been cleaning up the data, we've been getting some columns to convert it into formats that have nice methods that are easy to use. Now what we're going to do is actually run the search. To do that, we're going to search the FFI table for transient objects. So this is what I've been talking about, the two checks that we have to do. Check number one is to make sure that it's within the spatial extent. So we're just going to call this array one is we're going to take the rows, and I guess, sorry, before we dive right into this, I should talk about the structure. We're going to go through the entire table of transients. We're going to number them as we go along. And so when I'm calling row here, we're going through each row of the table. All right, so in this row, give me the SCI coordinate. Oops, sorry, I put an extra parenthesis there. Okay, so SCI coordinate. We're going to use this wonderful dot separation. Super convenient. And we'll do FFIs, SCI coord, close the quotation, close the bracket, less than 6 times u dot degree. Now, the nice thing about this is when we call FFI SCI coord, it's giving us the central coordinates of each FFI, but because we've called it this way, we're not looping through the FFI table, we're looping through the transient table. FFI's SCI coord will actually give us all of the coordinates all at once. And so when we do this dot separation, it will check all of those to see which ones are actually within this spatial footprint. The other thing that we'll do is create a second array, array 2, which is we'll use the row. We're going to hold the minimum start time. We need that less than or equal to the tmin of the FFI. I can get my correct close bracket. And we want the rows, the maximum start time from each. Once again, that is not a parenthesis, that is a bracket. So max start is greater than or equal to the FFI's t min. So again, this is the temporal overlap, provided that the maximum start time is greater than t-min, and if the minimum start time is less than t-min, that tells us that we are going to start in the range that we want, and we are going to see enough of this transient that we can probably do something interesting with it. Now, of course, there is one other thing that we have to do, which is to combine them, but we'll get there in just 1 second. For our convenience, or to satisfy our curiosity, we'll also record the numbers that we get here. So I'll take this n TESS, which we created before. We'll say that the I, the index number that we're on, is equal to the sum of array 1 and array 2. Then we'll do the next one, which this will then count the number that are in n test timed, which we have decided is the ones. Oops, sorry. I was looking a line ahead when I typed this. That doesn't make any sense. The first one is just the sum of array 1, because we're just figuring out how many FFIs contain the transient coordinates. The next one is where we're going to do that and. Sorry. So it's the next line, the timed one, is going to be where array 1 and array 2 are both true. Oops. And array 2 are both true. Because in this case, that means the thing that I've probably said more than you care to hear, but that it's both in the right place and in the right time. So I'm going to run this. Okay, good. I had some extra parentheses and I wasn't sure if Python needed those. But while this is running, you can actually see it's pretty quick, right? So as opposed to taking a second per query, doing our own table filtering and cross-matching is actually quite fast. And that's just because we're doing it slightly more efficiently. We already have the full table of FFIs, whereas if you send this request to MAST, it might be able to pull some of those results from the cache, but it just won't be as fast as us doing this special purpose search. Okay, well, it's already finished, so that's good. We've definitely saved some time with this. Let's take a look and see how many of our transient objects are in the field of view of the TESS observation. So we don't actually want the count. What we want is we'll do the sum, where the table, the n TESS values is greater than 0. And we'll do sum the table where n TESS, n TESS timed is greater than 0. So this shouldn't be too surprising. It seems kind of crazy that almost 8,000 of these overlap, until you again remember that TESS is an all-sky mission, and so it actually really shouldn't be that surprising that something that has surveyed most of the sky has found most of these, has been pointing in the right direction at least once. And in fact, we're probably, the reason it's not 8,700 something, really close to this, to the actual number, is because we took a shortcut. We literally cut corners. It did not include, sorry, that really by cutting those corners off, we've actually lost some of the results. So when you take a look at the ones where it was not only pointed the right way, but also at the right time, you can see that that drops pretty significantly by a factor of about 10. And that does make a little bit more sense, right? We shouldn't expect to be that lucky. All right, so we've filtered. We know that there are 837 of them. Now you could go and generate 837 light curves. We are just going to focus on one particular example, and you can actually find a full analysis in this paper here. So they presented a number of light curves on this. What we will do is just use this example. So we'll say the name is SN 2018 KOY. We're going to do another indexing. So we'll do an np.where, the table, the IAU ID is the name I've just typed above. Parentheses. We will create another row, or rather just get the row by doing table index I, and we'll print the row out. So this is the transient table from above. No special tricks here. We're just pulling out this particular target, which is, again, it's one of the 837. Feel free to double check me on that after this lesson. Now, since we only noted how many of them are correctly timed, we need to actually determine the sectors that they correspond to. And so we could have done something like, as we're doing this cross match, checking that if both of these things are true, just saving an observation ID somewhere, but something simpler is to just query for it, right? We have everything we need. We'll create a variable to hold some things. So first of all, the minimum start time, which we know from this, we've created a whole special column for it. So the minimum start time is just going to be this row. We'll do min start, and then we have to throw a 0 on here so it gives us just the value and not a whole bunch of other astropy table stuff. You can also do, I think a dot value would also be okay in this situation. We're also going to do a max start. We need that information to do a query. So row max start 0. And then actually that's enough. We've got the name. The target name is going to be TESS FFI because that's what it will be for all of these. And then what we're doing is filtering on tmin. So again, the start time of the TESS observation, we have our minimum desired and maximum desired start time, and so we can specify the range. So we'll create, we will create an obs table to hold our results. Observations.query criteria. The object name is name. The radius here is 0. We want an exact match. And if you're thinking to yourself, well, wait a minute, why don't we just search on the coordinates? Well, we could do that too. That would also be fine. But just as a proof of concept, you can't actually put something like a supernova name into MAST, and it actually will still get the job done. So it's just a cool feature. The obs collection is TESS. The target name is TESS FFI. And then we are going to do tmin. Now, the way to specify this is we need to do as a range. So we're going to do from min start to max start. And again, since it's a numeric value, we need to set high and lows for that. And that will get us back the ops table. Oh, actually, wait a minute. I don't think I typed anything wrong. I think MAST is just mad at me for, yep, there we go. I've done that query many times today, so maybe I was just getting blocked. But anyway, we've gotten back our result, and you can actually see right here, this is in sector 6. You can save this using the sequence number. I'm going to do that, even though we could just remember the number 6 is obs table sequence number. And we'll print it out. We have sectors plural, but it's just 6. You can imagine if you were doing this for more than one, you would want to know all of the sectors. Now we could open up this file. We could pass this to tesscut ourselves. I'm actually going to use lightkurve. Lightkurve has done a really good job integrating with tesscut, and it's just really convenient. There's no downloads. It works as it should on the cloud. We're going to use tesscut. To do that, we're going to redo our search a little bit, but it's easy. So search result is lk lightkurve dot search. We'll do search tesscut. We're going to pass in the name, our supernova name that I typed somewhere up here. And then we'll pass in the sector, which is sectors, but I'm going to type 6. So you could have used the variable that we saved above. I actually did want to look at that search result, so just hang on. Let's print that out. Search result. There we go. So we've got test sector 6, test cut, target name is there, distance is 0. That looks good to me. We want to download it, and it's not going to download it. And we also want to make sure that it's a 9x9 cutout. So 9 pixels by 9 pixels. That should be big enough for us to see our target and have enough pixels to establish a background. So if you're thinking, well, my target's not very bright, it'll only take up at most, like a 3x3 grid. Well, that's true, but you do need to do some background subtraction, as you'll see. So we'll say the size is 9. And we will do a target pixel file equals search results dot download all. Cutout size is size. Again, could have just type 9, but this is how we're doing it. And done. So it says that we've saved it locally, but actually this is not how lightkurve works. Oh, and I'm not in the correct directory. But if I were in the correct directory from the start, you would see there's nothing else in here. Nothing was downloaded. It actually loaded it right into memory, which is perfect. So there's a pretty efficient transfer of files, and it's not taking up any space on a cloud instance, or if you did this locally on your local machine. Let's check that the size of this makes sense. And I'm actually going to do just, I know it says a 0 index, but I'm just going to do the flux itself so we can see what this looks like. Oh, that's why I did the 0 index, because you can't just do the flux. I tried. Okay, there we go. So our target pixel file has 981 images, which are 9x9 pixels. That's what this is telling us. Those are the dimensions of the array. Let's take a look at the first and last images. So we'll do the first image, plot it. We will do the last image and plot that as well. Okay, so here's our first image, and the central pixel is somewhere around here, right? It should be right in the middle of this 9x9 grid. And in theory, if we've correctly identified the location of the supernova, then we should see something in the middle of this. So, drumroll please, dramatic reveal. Yeah, I can tell. Between this star here, there's nothing really that bright above it, but then certainly something has happened here. The brightness has definitely gone up. Now, we've got it by eye, which is good. So we've caught the supernova while it's brightening, since we went from dimmer to brighter. Because our target is extragalactic, there's no predefined aperture mask for this. So there's no way to automatically extract the brightness information. There's no way to take these images and turn them into a light curve. Fortunately, there is a method built into lightkurve that will do this for us. So let's start by, again, just proceeding with this assumption. The central pixel, that's where the supernova is. That's good enough. Let's try to make a plot. To do that, we'll start with setting up our central index. Now you could just figure out this number, but we're going to use a np.floor. We're going to divide it by 2, and we're going to do as type integer. So this will be robust if you change that size from 9 to something else. We're going to set target mask as np.full size. So again, this is just the size of our array, which is 9x9. We're going to fill it with false. So no pixels are selected. And then we are going to set the central element to true. So we're going to create a mask, target mask. Central index. Yes, close brackets equals true. So now we're selecting one pixel right in the very center. We'll also figure out how many pixels we've selected. Now, okay, you might be thinking that's trivial. We've only selected one pixel. But again, you can imagine that if you did this in a more complex example, this might be useful, right? If you were to pick more of them. So n target pixels is one, but let's compute it this way anyway. We're also going to plot the image. So TPF0 dot plot aperture mask equals target mask. So this will just make a nice plot for us. What we'll do then is create a light curve. So we'll say target pixel file 0. We can use the wonderful dot to lightkurve function. Set the aperture mask equal to the target mask. Cool. And then we'll also plot this while we're at it. Target LC dot plot. All right, so this is what we selected. This is the pixel right in the center. So that looks good to me. And down below, it should just sum up this brightness over time and make that into a nice light curve for us. And wow, oh my gosh, have we found the supernova? This is like crazy how bright it is. In fact, it's a little too crazy. I don't think we would expect this to get brighter by this factor of 9. TESS probably wouldn't be able to see it at that level of dimness and then suddenly have it spike up to this. I think that would probably be very bad news for Earth if TESS observed a star get 9 times brighter that rapidly. So this is an instrumental effect. It's probably due to scattered light as TESS is completing an orbit, or in the middle of its sector, it will turn in downlink data. So that's probably where this is coming from. It's almost certainly not a real signal. This is why we have to create a background mask. Fortunately for us, there is a method to do this. We can pass in our target pixel file and use this create threshold mask function. And you can set this threshold based on the percentile that you want. So this is setting it fairly low, but you'll notice it does a good job of picking out all of the dimmer pixels in this image. Now, we also need to take into account the fact that our signal is here. We've said that our signal is at this central pixel, which means that if we include it in the background mask, we're going to subtract a little bit of our signal out. Now, would it be enough to actually make a difference in the long run? Probably not, because we're going to average over all of these pixels, but let's clear it out anyway, just to make our signal a little more obvious. So I'm going to set the background masks here false, so that should take care of these 3 pixels. Do note that the index is opposite to how you view it because of how this is actually read in. The plot is making it look nice, but in actuality, the data itself is structured the opposite way. So this, I promise, will do the right thing. And in fact, we can take a look at our new mask, which we'll do with TPF 0 dot plot. Aperture mask is background mask. Mask color is white. Oops, the notation. Great. So you can see now this square in the center is clear. It's not being included in the background, which is good. To figure out what the background contribution is, we're just going to figure out what the brightness of all of these pixels added up together is, and then we're going to take the average. And actually, that will be more than enough for our purposes. So first of all, we need to know how many pixels there are in the background, and background pixels equals background mask dot sum. To normalize it, we're going to do background light curve per pixel is TPF0 dot to light curve, setting the aperture mask to the background mask. And then we'll just divide that by n background pixels. So we're getting a per pixel estimate there. The background estimate LC is then going to be the background LC per pixel multiplied by the number of target pixels. Oops, n target pixels. Now we only have one pixel, so we're multiplying by 1 here. But again, you can imagine if you were selecting more of these, you would need to compensate for the fact that if you have 2 pixels, you're going to have twice as much background as you would otherwise. So we'll run this, and we can plot our final light curve. Our corrected light curve is just going to be the target light curve minus the background estimate light curve. And we'll do a dot flux here. We're going to normalize this to the peak flux. So this is a bit different from what we've done previously. We'll create a peak normalized light curve, which is just the corrected light curve divided by the maximum, man max, corrected light curve flux. Okay, we're going to create 2 plots now to look at this. We'll do peak norm light curve dot scatter. So that's just the light curve, nothing else done to it. We'll also do a peak norm light curve dot bin. So we'll do time bin size is 6 times dot hour. So we're binning on a 6-hour cadence. And then we'll do scatter. We'll do a scatter plot, and I'm just going to make the points enormous so that they're easy to see. So if you look at this first plot, I'm convinced by that. That certainly looks like it's gotten brighter, right? It's a pretty obvious upward trend. And if you believe me that we've corrected for detector effects, then it should be pretty compelling. I actually find the binned version of this even more compelling. So if you bin this, that definitely looks like the brightness is going up for sure. And it's just when you remove all this noise, because it's such a faint target, you get this pretty clear picture. I would argue that you could maybe even bin it a little more if you wanted to. You could try 8 or 12 hours because we're going across this whole 27-day sector. We have enough data to burn, and the increase is slow enough that you can just keep binning to really try to bring that noise level down. It's also interesting to note the 2 lines here. So that the dotted line we put in at the half peak time, and this solid line we put in at what they think is the maximum. And to me, it looks like it's kind of already crested here, and it might even be on its way down. But this is a quick Jupyter notebook, and I think the paper went into a little bit more detail in their analysis. But just an interesting, that our different data processing method does kind of make it look like we've got slightly different result from them. So if you're interested, you can click on this, and it will take you to the paper in question. And there are figures in here that show. In fact, we might even be able to get to figure 35 if I can scroll to it fast enough. Yes, give me the high resolution. So this is it. This is what they published in their paper, and qualitatively, this does look pretty similar to what we have. So we've reproduced a result. There are some additional exercises down below if you just really want to get more supernova stuff. But those are just exercises to the reader, so do them if you feel so inclined. All right, that was a lot of talking and not a whole lot of pausing for questions or other things. So I do want to take a minute just to see if there are any questions from anyone in the audience. All right. I'm not seeing anything pop. Oh, yes, a mini question. Wonderful. Why not use something like, oh, TQDM. Yeah, there are plenty of libraries that will display very beautiful progress bars, and they're pretty nice. I like doing the print statement stuff. I like having control over that part of the code that I write, but there's no reason why you couldn't use a package like that if that's what you prefer to use. Um, I have on occasion with certain packages, depending on the complexity of the task, run into issues with it like not quite displaying the progress bar how I want it, or like displaying multiple progress bars. And so I just tend not to use it. But again, there's no reason why you can't. All right. Well, if there are no other questions, I've got a thumbs up. Thank you all for joining us for the late night session. Thank you for putting up with my bad jokes, with my puns, and and finding them funny myself. Um, Thanks as always for attending, and I hope to see you all next week at the next webinar.